Next, I'd like to remind you how our motor driver works. For this class, we're using a DRV 8835. The main specifications that we liked about this one were that it was 2 channels, meaning it can control 2 separate motors at the same time. It has 1.2 amps per channel, which is well over what our DC motors will ever pull. And it has a voltage rating for the motors in the 0 to 11 volts, and a logic rating, I think it was in the 2 to 7 volt range. So all those parameters make it a good candidate for what we need for this class. The motor driver itself has 14 pins, so 7 on either side. The top left and top right pins were both ground. And that's usually denoted on the board by having a square solder pad instead of a circular solder pad. Those were both ground pins. Next, on the left side, was VCC. So that's the voltage of our logic units. So it knows that your microcontroller, which we'll draw over here in a little bit, it'll have a certain amount that it considers, a certain voltage level that it considers for a 1. And that's 3.3 volts, and a 0, which is 0 volts. There are other systems where a 1 is 5 volts, and if the two systems don't agree on what high is, you can have a situation where the microcontroller outputs 3.3, and another system is considering that a 0 because it's not close enough to what it considers the 1 signal. And the next pin on the right side was VM. That's the voltage that's actually applied across the motor terminals. So if I go back a few slides, that's the voltage that the motors would see at Vin. Next, on the left-hand side, we have pairs of pins. And I'm realizing now I should really draw those as circles to match what the actual board has. Although my spacing here is not going to be what the board is either. Same on the output, we have pairs of pins. And this one here we're just going to ignore. It doesn't come into play for how we're using this particular H-bridge. On the left-hand side is a mode pin. And we're always going to set that to high. And what that looks like for our breadboards is we're essentially connecting across that gap. So that mode is always brought high, and that puts us in what's called phase enable mode. And looking at the diagram, this actually is Vin. As for the control connections, we have the B motor and the A motor. Each of those have an enable pin and a phase pin. And just as a reference, I'll remind you what those pins do. The enable pin is used for controlling speed, and the phase pin is used for controlling direction. This one's a PWM input, and we'll look at that in the next couple of slides. And direction is just a GPIO pin, meaning you can expect to either set it high at 3.3 volts or low at 0 volts. On the output side, we have 2 outputs per motor, and they correspond to the same inputs on the other side. So we have the B motor output and the A motor output. I'll just draw a simplified version of the motors. I don't like that diagram. Make a small change to it. So depending on what values we supply on the input side, the output current direction could be in this direction or in this direction, depending on which way we want the motor to spin. Likewise, the current level, so how large of a value. Is I closer to, let's say, 20 milliamps versus 100 milliamps? That will control the speed of the motor. And for completeness sake, I should really fill in the rest of this diagram. We'll have our battery with a positive side and a negative side, the negative connected to ground, and the positive connected to VN. On the opposite side, we have our microcontroller. And we'll have 6 pins connecting over to the motor driver from our microcontroller. It'll have a ground output pin, a 3.3 volt supply pin. That's actually not coming directly from the microcontroller itself. It's coming from a voltage regulator on the same printed circuit board as the microcontroller. But in addition to those 2 pins, we'll also have the 4 pins connecting to the A and B motor channels. And I'll draw them spaced out just so it's easier to draw my wires. But that's not exactly how they are laid out on the board themselves. Our grounds are connected. Powers are connected. We'll have a enable pin for each motor and a phase pin for each motor. Something left off of this diagram, which I'll bring up later, is that we actually have more computation on the motor side itself. There's a little magnetic disc attached to the motor shaft, and as that rotates, there are a couple of extra sensors. I'll blow this up later. A couple of extra sensors called Hall effect sensors that are measuring the rotation of the motor shaft, and those are also connected back to the microcontroller so that we can sense how fast the motor is going. Before we dig into the encoder, though, let's actually look at how the H-bridge works in greater detail. I'm going to ignore the logic side for this next diagram, and we'll really just focus on the output. In fact, we'll really just focus on one motor. I'm only going to show one H-bridge instead of 2 H-bridges. It'll be easier to show a diagram for one than both on the same slide here. Internally, inside the H-bridge, there are 2 of these. We've got out 2 and out 1. Those are connected to transistors. And I'm realizing an inaccuracy. I really shouldn't label these out 1 and out 2. That's really what I should label these points here. Internally, these pins would be connected to VN and ground. I'm going to draw these as switches, but they're actually transistors, which are electrically controlled switches. But drawing them as switches mean I can put in a lot less detail, which is useful for the abstraction level that we're going with here. I'll label both of these sides. We'll call one side the clockwise direction and the counter or anti-clockwise direction. On one side, we'll close 2 of the switches. So we'll call that closed and that closed. And we'll leave the others open. So in this configuration, power will flow from VN and be ready on this pin. And it'll flow through the motor. And so in this case, we can get the motor to spin in a clockwise direction. On the other side, if we electrically close the other 2 gates or switches and leave the other ones open, we'll have the opposite spinning motor axle. So one positive of this system is that we never have to reconnect our batteries. In both cases, we have positive on the upper terminal and negative on the lower terminal. But we can still get current to flow in opposite directions, meaning we can control the direction that the motor is spinning. The last point you might be wondering is, how do we control the speed at which the motor is spinning? And this is where I should be a little bit more careful, and we're not actually passing in Vn here. Instead, we're passing in Vn, and it's being pulse modulated. Same on this side. And I'll draw a slightly different type of pulse train. So what is pulse width modulation? It's a way for us to fake having an analog signal. The particular microcontroller that we're using in this class has a bunch of pins on it. They'll be labeled something like GPIO. Some of them are labeled SDA, SCA, MOSI. We have some serial connections. There's even a an analog to digital converter. Meaning we can read an analog signal. What most microcontrollers don't bother with is producing an analog signal. And by analog, I mean the output can vary at levels that are more than just 0 and high. We'll call that 1, which for our microcontroller is 3.3 volts. You might expect that you could set the output of a digital pin, a GPIO pin, to something like, I don't know, 0.2 times 3.3, so 20% on. That's not something we can do on our microcontroller. So we can't generate a signal that goes up and down, and we certainly can't create negative voltages. Instead, we do something called pulse width modulation to fake this analog signal. It's a technique that works really well when you're dealing with a physical system, something like a motor that acts at a much slower scale, a much slower speed than we can turn on and off a switch. So a pulse width modulation, you're typically dealing with a square wave. And what I've drawn here, or trying to draw on here, is something that you would call a 50% duty cycle square wave. If you were to average this signal across time, the average voltage output would be 50% whatever the peak voltage is. So in this case, the average would be 3.3 volts divided by 2, because it's on for 50% of the time and off for 50% of the time. If we wanted a 0% duty cycle or a 100% duty cycle, Those are pretty simple to draw. The 0% is just always low, which would be 0 volts. And the 100% duty cycle, so if this is my scale, would be always on. And the result would be 3.3 volts. Clearly I could have something in between. And I'll clear off some space here. And just delete these less interesting signals. I could have something like a 75% duty cycle, which would be on for 75% of the time. And our result there would be an average that's not quite at 3.3 volts, but more than 3.3 over 2. For your motor, it's going to behave as if you were applying 75% of the maximum voltage across it when it sees something like this, 75% duty cycle on. So back to this diagram, that's really what I'm referencing here when I show the pulse train. Vn, on the peak of Vn, is always going to be whatever our battery voltage is. So in this case, our battery's nominal voltage is 3.7 volts. So the peak of Vn would be 3.7. If I do 50% duty cycle, then the voltage, the effective voltage across the motor, would be 3.7 divided by 2. Jumping back to here, that's exactly the signal that's being sent on the enable pin. This is a PWM signal, and it's used to connect Vn to one of your two outputs. Whenever the signal is high, here, Vn is connected to one of your outputs here. So we get direction on these purple lines, which will flip your switches, and we get speed over the orange lines, which tell you when you're actually connecting Vn to the outputs. The last piece of the puzzle that we'll cover before we can start talking about how to actually write a control algorithm for your motors are the quadrature encoders. The motors we're using have this nice motor header, and for the most part I've just been having you connect it up without having to worry too much about what's actually going on for each of the pins. If we were to now delve in to that header and look at each of the pins, the outermost pins are M1 and M2. And those are exactly the pins that are connected across the motor. So your PWM signal is coming into here. And so that's going to control the speed and direction of the motor. If I have positive voltage on this side, it'll spin one way. If I have positive voltage on this side, it'll spin the other way. Depending on the duty cycle, I can increase or decrease the voltage, the rate of spinning on the motor. The next pins are ground and VCC. And this particular interface, it likes to put those on sort of opposite sides instead of right next to each other like the other boards that we've been dealing with. The final two pins on that board are labeled C1 and C2. As far as I know, it's more common to call those the A channel and B channel, so I'm actually going to change the name here so that I can be consistent with what I've seen it referred to as in other places. If I were to draw a diagram of what's actually going on the back of the motor here, it would look something like this. You have your axle sticking out the back of your motor, and attached onto that axle is a black disc. That black disc is actually a magnet with a north and south pole. And that magnet, since it's attached to the axle, will rotate in either direction. Next to the magnet are a couple of sensors. These are called Hall effect sensors. Hall effect sensors have quite a few uses. The one most pertinent to our case here is to detect transitions from a change in a magnetic field. So as this north side of the magnet transitions to south, so let's say we're rotating in the clockwise direction, at some point this north part will come all the way around, and the south part here will be what's next to the Hall effect sensor. The Hall effect sensor will detect that change, and it'll send a little voltage pulse across one of the pins here that's then read by our microcontroller. And since we have two of these, we can do more than just measure the speed. Actually, I'll take one step back. If we did only have one sensor, we would only be able to detect the speed of the motor, because we wouldn't know if the transition was because the motor was spinning counterclockwise or if it was spinning counterclockwise, or if the motor was spinning clockwise. With just a single sensor, we wouldn't be able to get that. With two, we can detect when we transition from south to north, and that'll ping one, and then 90 degrees out of phase will ping the second one. That's why I have these drawn sort of off the center axis here. They're actually specifically positioned so that the two will be 90 degrees out of phase with one another. And by 90 degrees out of phase, I'm talking about this diagram I'm about to draw. As we start rotating the axle, we'll start getting pulses out from one of the Hall effect sensors. And that'll look like another square wave. We're essentially detecting when the north pole is facing the sensor. If we're 90 degrees out of phase, we've spaced out our Hall effect sensors correctly. The second sensor will appear like so. And let's assume it wasn't moving before this, so we weren't getting any pulses before that time. So on our microcontroller, we'll be reading these two signals from the A and B channels. If we detect this positive edge on the A channel, so going from 0 up to 3.3 volts, and then some amount of time later we detect a positive edge on the B channel, we'll know that the motor is moving. And we can actually detect the direction it's moving as well. And I'll show that by drawing a second set of axes below the first two. In the second scenario, we essentially see the same thing on, you can pick whichever channel you want to focus on, because each channel is really only detecting one thing, which is when is the North Pole, or depending on how the Hall effect center is oriented, the South Pole, when the North Pole is facing that sensor. In this second case, though, instead of seeing the rising edge halfway through pulse A, we'll see the trailing edge. Which means it would have had to have started pulsing before the A channel. The way the library is written for this is you just dedicate, or you mention that one of the inputs, you're going to track the rising edges and use those to say, essentially get an idea of what the speed of the motor is. And so if I draw that same thing on the other document, or sorry, the other set of plots, you'll notice the difference here, the difference that we're recording. And that second bit of information will tell you the direction. So how fast these pulses come will give you speed, and the relationship between the two separate signals will give you the direction. You won't be asked to write code for this. In fact, our microcontroller, our ESP32S3, has what's called a hardware PCNT on it, a pulse counter. And so I'm not actually writing code to determine this in software. Instead, it's just built into the hardware itself. There are some latches that you can configure to count your pulses and it'll give you essentially a count of how many pulses happened within a certain amount of time. And you can use pulses per time and relate that to speed by knowing how many pulses you expect on each rotation. And that's built into the library that I'm providing for everyone. All right, the next thing we'll talk about is how do we actually design a control system for our motor and motor driver.